In this video, we'll talk about how to evaluate infinite limits by factoring. So first, let's review a few types of functions that we're going to encounter. So a polynomial has the form f of x equals an times x to the n, where n is some non-negative integer power, and then plus a sub n minus 1 times x to the n minus 1. Plus dot dot dot, it would keep going like this up until plus a sub 1 times x, and then finally just some constant term, a naught, where the a naught, a1, comma dot 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 up until an are reals, and then the n is a non-negative integer. All right, a rational function is a function of the form polynomial over a polynomial. Maybe I'll call this one g of x. Okay, and let's give an example. So e.g., g of x equals 2x minus 7, that's a polynomial, divided by x squared, another polynomial. That would make a rational function. And now let's do what I'm going to call a rational-like function. And the easiest way I can describe this is by giving an example. So if I had a function like 2x minus 7, but now in addition to just letting the powers of x be non-negative integers, I'm going to allow things like fractions. So if I had a cube root of x, that is actually, let me write that better. If I had a cube root of x, that's x to the 1/3, I have a fractional power, and then plus 1. This is the type of thing I'm going to call a rational-like function. The more technical term for functions like this, they're also called algebraic. But the ones that we're going to see are going to look so similar to rational functions, which is why I'm calling them rational-like. All right, let's look at an example. Let's find the limit as x approaches infinity of negative 2x to the third minus 5x plus 4. So our idea is going to be to first factor out the highest power of x. It'll turn out that as x gets really, really big, the highest power term grows a lot more quickly than any lower power terms. So we're going to try to use that. We're going to try to leverage that. So I'm going to evaluate this limit as x goes to infinity. Let's factor out that x to the third. When we do, we'll get a minus 2 first. And then we'll get minus 5x over x to the third. That's what I'll have if I factor out x cubed from the minus 5x. I just divide by x cubed. And then I'll get plus 4 over x cubed. Let's simplify that middle term. That middle term would become minus 5 over x squared. And now, from here, let's go ahead and plug in. So that'll give me infinity cubed times negative 2, and then minus 5 over infinity squared plus 4 over infinity cubed. Okay, and I can simplify this further. This is infinity cubed. Well, actually, so infinity cubed is infinity times infinity times infinity. That's still going to be huge. That's going to be infinity. And then I get minus 2. And then minus the infinity squared on the bottom is infinity. So 5 divided by a huge, huge, huge number is going to be something super close to 0. So this fraction is approaching 0. For the same reason the next fraction is approaching 0, I get plus 0. Okay, so overall I have infinity times negative 2, which is negative infinity. And that is my answer. So I want to notice that the highest power, which was that minus 2x cubed, that dominates. In fact, even if I were to just have ignored all the other terms and just sort of plugged in infinity straight up into just that negative 2x cubed, it actually would have given me the same answer. And we'll see that idea later when we talk about a shortcut. But for right now, I don't want to use that. Okay, so now this was a polynomial. For the limit as x approaches plus or minus infinity of r of x, where r of x is either a rational or rational-like function, we will factor out the highest power of x from the numerator and from the denominator. And then, from there, we use logic like we did here when plugging in and simplifying. Let's look at another example. So in part A, I want to evaluate the limit as x approaches negative infinity of 3x minus 4x squared plus 7 on top over 2x plus 5 on the bottom. So before I get into simplifying this, if I use my idea from before about the dominating terms, the biggest power on top is this minus 4x squared term. The biggest power on the bottom is 2x. If I were to just plug into those, I would end up with minus 4 times negative infinity squared on the top. On the bottom, I would end up with 2 times negative infinity. So negative infinity squared is going to be positive infinity. Multiply that by negative 4, that's negative infinity. And then 2 times negative infinity is negative infinity. I cannot just cancel these infinities and say that this is 1. That doesn't work because infinity isn't a number. I can't just cancel it on the top and the bottom. The infinity that I have on the top and the infinity that I have on the bottom both just represent a huge number, but they might not be the same number, so I can't cancel them. Okay, but the key thing I wanted to point out about this is an indeterminate form. Infinity over infinity, or even with pluses or minuses, indeterminate form. So I need to simplify. And that's why we are even bothering with trying to do stuff like factor, because we have an indeterminate form. All right, so let's use our strategy. Let's take the limit as x approaches negative infinity, factor out the biggest power of x on the top and the biggest power of x on the bottom. On the top, that's x squared. And if I factor it out from the first term, I'll be left with 3 over x. I could check it if I distributed x squared back to that term. I would get 3x, which is good. From the next term, I'll be left with minus 4. From the last term, I will have plus 7 divided by x squared. Because I'm factoring out x squared, I need to divide that term by x squared. Okay, and on the bottom, I'm going to take out x. That's the biggest power. The first term will be left with a 2. And then from the next term, I'll have to divide it by an x to be left with 5 over x. All right, so from here, we get the limit as x approaches negative infinity. Now I can do a little bit of cancellation. This x on the bottom will cancel with the x squared to leave me with an x. So we'll have x times 3 over x minus 4 plus 7 over x squared all over 2 plus 5 over x. So we've simplified a little bit. Now we're going to try to plug in into the x gives me negative infinity. And then I'll get 3 over x, 3 over negative infinity minus 4 plus 7 over negative infinity squared over 2 plus 5 over negative infinity. Alrighty, so we have negative infinity times 3 divided by negative infinity is going to be 0, minus 4. And then 7 over negative infinity squared also is getting super, super close to 0. I'll put a plus 0 because the sign of this is going to be positive. And on the denominator, we have, let's see, 2 and then 5 over negative infinity. That is getting really, really close to 0. Okay, so overall, if we simplify this a little bit, we have negative infinity and then times negative 4 divided by 2, which is negative 2. Negative infinity times negative 2, that is positive infinity. And that is our answer. That is what this limit is. Okay, let's look at another example and see if we can apply this strategy. Part B. For this, I want to first give you a couple of minutes to try it on your own. So pause the video for 3 minutes to try this one on your own. 4, 3, 2, 1. Pause it for 3 minutes to try part B. Alrighty, so hopefully you did that. Hopefully you paused it for about 3 minutes to really try this question. Let's talk about it together. So on the numerator, I can go ahead and just factor out that highest power, that x squared. On the denominator, it'll help if I can distribute this out first, so I can more clearly see that highest power term. And if doing that, I get 16x squared. And then I'll get 5 times 8x, that is 40x. And then 2x times -1, that's going to be minus 2x. So 40x minus 2x, that's plus 38x. And then the last two terms multiplied will give me a minus 5. All right, now let's do our factoring. This is the limit as x approaches infinity. Factor an x squared out of the top. So from the 3x, if I factor out an x squared, I divide this by x squared, which will give me 3 over x. From the next term, I'll be left with minus 4. From the last term, plus 7 over x squared. And on the bottom, let's also factor out an x squared. That's the biggest power of x on the bottom. That'll leave me with 16. And then plus, if I divide 38x by x squared, I'll get 38 over x. And then for the last term, minus 5 over x squared. Okay, and this one is extra nice, I would say, because the x squareds cancel perfectly. Now let's go ahead and try to plug in. So if I do that, I'll get 3 over infinity first, which is getting super close to 0, and then minus 4, plus 7 over infinity, which is also getting really close to 0, over 16, and then plus 38 over infinity, also getting close to 0, and then minus 5 over infinity, which is getting close to 0. So I'll put a minus 0 just because I see a minus sign in front of that fraction. Okay, now simplifying this, we get negative 4 over 16, which is negative 1/4. And that is our answer. That is what this limit is. Okay. So next I want to give it definition. And the definition says my function f has a horizontal asymptote at y equals L if either the limit as x approaches infinity of my function equals L, or the limit as x approaches negative infinity of my function equals L. Okay, so for part B, in terms of the picture, if I were to draw some axes, and I were to put negative 1/4 on the y-axis, what's happening here is as x approaches infinity, meaning as x gets really, really big, the y values, or the outputs of the function, are getting super close to negative 1/4. And it turns out that they are getting close to negative 1/4 from sort of above it. If I were to use a graphing calculator, it doesn't really matter in terms of what I'm about to say next, but it turns out it's getting really close to negative 1/4 from above. But what's happening is it is asymptoting. As x gets really, really big, the y values get super, super close to this number. That is going to be our definition of a horizontal asymptote. So the function in part B has a horizontal asymptote at y equals negative 1/4. If I wanted to find all of the horizontal asymptotes, I would also need to take the limit as x approaches negative infinity. Well, let's write that better. As x approaches negative infinity of our function as well. All right, let's do one final example in this video. Part C, we have this limit as x approaches infinity, and this time the numerator is 3 square root of x minus 4x squared plus 7, and the denominator is 2x to the 5 minus 8x. Okay, so first let's rewrite the square root as a power. This is x to the 1/2. And now I can use the same idea. We can hone in on the biggest power of x on the top and the bottom and factor those out. So we'll get the limit as x approaches infinity. Biggest power of x on the top is x squared. So when I factor that out from the first term, right now it's 3x to the 1/2. And I will have to divide that by x squared because I'm factoring that out. From the next term, I'll be left with minus 4. And then from the last term, plus 7 over x squared. On the denominator, let's take out an x to the 5. So from the first term, that'll leave me with a 2. And then from the next term, it'll leave me with a, if I couldn't see what's going to be left over without simplifying, I could write it as 8x over what I just took out, over x to the 5. Okay, but now let's simplify a little bit. This equals the limit as x approaches infinity. Well, let's see, I can cancel an x squared here and here. That'll leave me with x cubed on the bottom. And then I can also cancel an x to the 1/2 with this x squared and be left with x to the 3/2. So we get 3 over x to the 3/2 minus 4 plus 7 over x squared over x cubed in front of the parentheses and then 2 minus, and I can also cancel an x with the x to the 5 and be left with x to the 4 minus 8 over x to the 4. And now let's go ahead and plug in. So doing that, we will get 3 over infinity first, which is getting close to 0, minus 4, plus 7 over infinity, which is getting close to 0, over, and then we have infinity cubed, and then times 2 minus 8 over infinity, which is getting close to 0. So overall, we have a minus 4 on the top. On the bottom, we have 2 times infinity, because infinity cubed is infinity. And 2 times infinity, that is infinity. Okay, so negative 4 divided by infinity, that is 0, because it's getting super, when I divide negative 4 by a huge number, it's getting really, really close to 0. And that's my answer. In terms of our goals for this section, we've now discussed how to evaluate infinite limits using factoring. In the next video, we'll introduce a shortcut for doing these infinite limits. But it's really important that you understand how to do it this way, how to do it by factoring.